Out there in the vast silence of space, hidden among the swirl of galaxies and the glow of distant stars, something extraordinary is pulsing. Imagine a beacon so powerful it cuts through the darkness, sending out signals with the precision of a ticking metronome, except this metronome is a cosmic powerhouse, spinning faster than a blender on its highest setting. These are pulsars, the universe's natural lighthouses, and they might just hold secrets we've only begun to dream of. Picture this: you're tuning a radio, scanning through static, when suddenly you catch it, a rhythmic pulse, repeating like clockwork. No, it's not a glitch or some stray transmission. This is the heartbeat of a dead star, a neutron star so dense that a single teaspoon of its material would weigh as much as a mountain here on Earth. When these stars spin, they send beams of radiation sweeping across the cosmos, flashing like a cosmic strobe light, and here's the wild part: they're so regular, so predictable, that scientists initially mistook them for signals from an alien civilization. That's right, the first pulsar discovery in 1867 had astronomers wondering if they'd just intercepted a message from another world, but the truth is even more fascinating. These pulsing giants aren't just celestial oddities, they're cosmic laboratories, pushing the limits of physics as we know it. Their gravity bends space-time itself, their magnetic fields could strip the data from your credit card from halfway across the galaxy, and their pulses. They might just be the universe's way of sending us a message we're only starting to decode. Could these rhythmic signals be natural phenomena, or is there a chance, however slim, that there's something more? That's the mystery we're unraveling today. From the moment they were discovered to the cutting-edge research happening right now, we're diving deep into the language of pulsars, exploring what they're telling us and why it might change everything we think we know about the cosmos. So get ready, because this isn't just a story about stars, it's a story about how we listen to the universe and what it might be saying back. To understand how a pulsar flickers into existence, we have to rewind to the final, cataclysmic moments of a massive star's life, a star at least 8 times heavier than our Sun. When such a star runs out of fuel, its core collapses in on itself in a fraction of a second, triggering a supernova explosion so bright it can outshine an entire galaxy. But the real magic happens in the aftermath. What's left behind isn't just a cloud of glowing debris, it's a neutron star, an object so dense that the protons and electrons in its atoms have been crushed together into neutrons, packed shoulder to shoulder in a sphere no bigger than a city. Now here's where physics gets wild. As the star collapses, it starts spinning faster, just like a figure skater pulling in their arms to accelerate. But in this case, the skater is a cosmic powerhouse, shrinking from the size of a star down to a speck just 12 miles across. That sudden contraction sends it whirling at dizzying speeds, sometimes hundreds of times per second. And that's not all. Its magnetic field, already intense during the star's life, gets squeezed and amplified to mind-boggling strengths, trillions of times stronger than Earth's. This magnetic field acts like a cosmic lighthouse, focusing radiation into narrow beams that blast from the star's poles. Because the star's rotation axis and magnetic poles aren't perfectly aligned, these beams sweep across space like the spinning beam of a searchlight. When one of those beams crosses Earth's path, our telescopes pick it up as a pulse of energy, a rhythmic flash of radio waves, X-rays, or even visible light. That's why we call them pulsars. They're not just spinning neutron stars, but neutron stars that happen to wink at us with perfect cosmic timing. But their precision isn't just impressive, it's downright eerie. Some pulsars are so consistent, their pulses arriving with the regularity of atomic clocks, that the first one discovered, CP 1919-1, was jokingly labeled LGM-1 Little Green Men, one because astronomers genuinely wondered if they'd stumbled upon an alien transmission. Of course, the truth was even stranger. a natural object forged in stellar violence, keeping time better than any human-made mechanism. So why don't all neutron stars become pulsars? The answer lies in geometry. If the beams don't happen to sweep past Earth as the star spins, we'll never see their pulses, meaning there could be countless more of these cosmic lighthouses out there, silently flashing in directions we can't see. But for the ones we do detect, every pulse is a message, a clue written in the language of gravity, spin, and magnetic fields. And as we decode that message, we uncover the secrets of matter pushed to its breaking point, where the laws of physics as we know them start to bend under pressures we can barely fathom. The lighthouse effect is the cosmic choreography that makes pulsars blink at us with such eerie precision. Picture a spinning top, wobbling as it rotates, except instead of a child's toy, this is a super-dense neutron star, its magnetic poles tilted away from its axis like a leaning tower. As it whirls, charged particles race along those magnetic field lines, accelerating to nearly the speed of light until they erupt in focused beams of energy from the star's poles. These twin jets don't just spray randomly into space, they sweep across the cosmos like the rotating beam of a lighthouse, slicing through the darkness with every spin. When Earth happens to lie in the path of one of those beams, we catch a fleeting but regular pulse of radiation, sometimes in radio waves, other times in X-rays or even visible light. Take the Crab pulsar, the rapid-fire remnant of a supernova observed in the year 1954. It spins 30 times every second, and with each rotation, it shoots out a visible flash so bright you could almost see it with the naked eye, if your reflexes were quick enough to catch a blink lasting just 30 milliseconds. That kind of precision isn't just impressive, it's cosmic clockwork, rivaling the most accurate timekeepers humans have ever built. But pulsars aren't always perfectly predictable. Sometimes they stutter, a glitch occurs when the star's crust, a crystalline layer barely a kilometer thick, suddenly cracks under unimaginable strain, causing the pulsar to speed up by a fraction of a second. These starquakes offer scientists a rare glimpse into the star's interior, where matter is crushed into exotic states no lab on Earth could replicate. Other pulsars slow down gradually, their spins ebbing as they bleed energy into space, their magnetic fields acting like cosmic brakes. And then there's the tantalizing question, could these flashes be more than natural phenomena? Some researchers have toyed with the idea that an advanced civilization might harness pulsars as galactic signal fires, tweaking their pulses in ways that stand out against the background rhythm of the universe. It's a long shot, but in a cosmos full of mysteries, the line between natural wonder and potential message can blur in the most intriguing ways. After all, if you want to send a signal across thousands of light years, what better beacon than a pulsar's unmistakable, universe-piercing flash? Among the cosmic orchestra of pulsars, the millisecond pulsars are the virtuosos spinning so fast they blur the line between astrophysics and science fiction. These celestial metronomes whirl hundreds of times every second, their pulses arriving with a precision so exact they rival the atomic clocks we use to define time on Earth. But how does a pulsar, born from the violent death of a star, become such a finely tuned timepiece? The secret lies in a cosmic heist. Millisecond pulsars are thought to start as ordinary, slower spinning neutron stars with a fortunate twist, a neighboring star close enough to share its material. As gas from this companion star spirals onto the pulsar, it transfers not just matter but something even more valuable, angular momentum. Like a figure skater pulling in their arms to spin faster, the pulsar accelerates with each sip of stolen material, revving up over millions of years until it's spinning faster than a kitchen blender at full throttle. By the time the feast ends, what's left is a stripped-down stellar corpse, now a hyper-fast beacon flashing with mind-bending regularity. This precision isn't just a curiosity, it's a tool. Because their pulses are so predictable, millisecond pulsars act as cosmic laboratories for testing Einstein's theory of general relativity. When gravitational waves ripple through spacetime, they stretch and compress the fabric of the universe ever so slightly, causing the pulses arriving at Earth to drift by fractions of a millisecond. By monitoring these tiny timing shifts across an array of pulsars, scientists have detected the faint hum of gravitational waves from colliding supermassive black holes, a discovery that earned the Nobel Prize in Physics in 2017. And the potential doesn't stop there. Imagine a navigation system so vast it spans the galaxy. Pulsar timing could one day guide spacecraft with pinpoint accuracy, using the steady pulses of these distant lighthouses as cosmic GPS satellites. NASA's NICER experiment has already tested this concept aboard the International Space Station, proving that pulsars could be the ultimate deep space beacons. But the most tantalizing possibility, that some of these pulsars might not be entirely natural, their flawless rhythms have sparked speculation. Could an advanced civilization tweak a pulsar's spin to encode information, turning it into a galactic billboard? Projects like SETI have scoured pulsar signals for unnatural patterns, searching for anything that might hint at intelligent design. So far, every pulse has a natural explanation, but in a universe this vast, the line between coincidence and communication might be thinner than we think. After all, if you wanted to send a message across millennia, what better medium than a clock that never stops ticking? On the evening of August 15, 1977, something extraordinary happened, a blip in the static that still haunts astronomers to this day. The Big Ear radio telescope in Ohio picked up a signal so intense, so unlike the usual cosmic noise, that the researcher reviewing the data circled it in red pen and scribbled, "Wow." Next to it, that 72-second burst of radio waves, centered around the frequency hydrogen emits naturally in space, burned brighter than anything else ever detected, and then vanished without a trace. Decades later, no one can say for certain what caused it, but here's where pulsars add fuel to the fire. Hydrogen isn't just the universe's most abundant element, it's also a logical bullseye for anyone trying to send a message across the stars. It's the cosmic equivalent of broadcasting on a channel everyone's already tuned to, and while the WOW signal's brevity makes it hard to pin down, some researchers have pointed out that certain pulsars emit energy eerily close to that same frequency. Could it have been a pulsar's beam, briefly amplified by some interstellar quirk, or something more deliberate? The timing is suspiciously precise. Pulsars are nature's most reliable timekeepers, but their signals can be warped by passing through clouds of gas, or distorted by the gravity of unseen objects, effects that might explain why the WOW signal was never heard again. Yet there's another more provocative possibility. What if pulsars aren't just cosmic lighthouses but cosmic relays? Their sheer power and predictability make them ideal candidates for a sort of interstellar semaphore system. An advanced civilization could, in theory, modify a pulsar's emissions briefly to encode information, knowing its pulses would travel vast distances with perfect clarity. Projects like SETI have scoured pulsar data for patterns that might hint at artificial tampering, tiny irregularities in timing or frequency that don't fit natural models. So far, nothing conclusive has turned up, but consider this: if you wanted to send a message that would last millennia, surviving long after your civilization crumbled, wouldn't you piggyback on something immortal? Pulsars outlive planets, they outlive stars, they might even outlive entire galaxies. The WOW signal might forever remain a mystery, a cosmic flare in the dark, too fleeting to decode. But every time a pulsar's rhythm flickers, every time its beat shifts in a way we can't quite explain, it sparks the same tantalizing question: are we listening to the universe's heartbeat, or could we, just maybe, be overhearing a conversation? In the cosmic graveyard of a dead star, something impossible came to life: planets. Not just any planets, but worlds orbiting the corpse of a stellar giant, bathed in lethal radiation and lashed by gravitational forces that could shred a normal world to dust. This wasn't science fiction. In 1992, astronomers Alexander Walskzen and Dale Frail pointed their radio telescope at a distant pulsar, FRBs 257+12, and found the first exoplanets ever, confirmed 3 of them, dancing around a stellar remnant spinning faster than a power drill. These weren't gentle, Earth-like havens, they were survivors of apocalypse. When the pulsar's progenitor star went supernova, the explosion should have vaporized any nearby planets. But somehow, against all odds, new worlds coalesced from the ashes. Picture this, a disk of supernova debris, rich with heavy elements, swirling around the newborn neutron star. Over millions of years, gravity sculpted that rubble into planets, alien worlds forged from stellar wreckage. The smallest of them, at just 0.02 times Earth's mass, was nicknamed Draugr, after the undead of Norse myth. A fitting name for a world born from death. What must it be like on the surface? Imagine standing under a sky lit not by a sun, but by the haunting strobe of a pulsar, its beam slicing through the darkness every 6.2 milliseconds. The radiation alone would be deadly enough to strip away atmospheres and bombard the ground with X-rays, and yet, Earth has shown us life's stubbornness. Extremophiles thrive in nuclear reactor waste, in boiling acid, in the crushing depths of the ocean. If life could cling to existence near a pulsar, it might look nothing like us. Perhaps organisms with crystalline skins to deflect radiation, or buried deep in subterranean oceans, shielded by miles of rock. Then there's the tantalizing thought, could intelligence arise here? A civilization perched on a pulsar planet would have a front-row seat to the universe's most precise timekeeper. What if they learned to manipulate its pulses, encoding information in the flickering light? It's a wild idea, but consider this: humanity already uses pulsars as navigation beacons. In 2018, NASA NICER experiment used pulsar X-rays to guide the ISS with galactic GPS. An advanced species might take this further, turning their pulsar into a cosmic telegraph, its rhythms carrying messages across the void. The real wonder isn't just that these planets exist, but what they force us to reconsider. If life can emerge in the aftermath of a supernova, where else might it hide? Pulsar worlds rewrite the rules, proving that even in the harshest corners of the cosmos, nature finds a way, and with it, perhaps the potential for voices calling out in the static, waiting to be heard. 2 dead stars locked in a gravitational embrace, circling each other with such precision they rewrite our understanding of the cosmos. This is the breathtaking reality of binary pulsars. Picture a cosmic ballet where each partner weighs twice as much as our sun, but spins hundreds of times per second, their rhythmic pulses acting as flawless timekeepers even as they whirl through space at a fraction of light speed. The first of these pairs, PSRB 1913+16, discovered in 1974, became one of the most important laboratories for testing Einstein's theory of general relativity. Over decades, astronomers noticed its orbit was shrinking by 3 millimeters per year, not because the pulsars were losing energy, but because they were radiating it away as gravitational waves, ripples in spacetime itself. This discovery, which earned Russell Hulse and Joseph Taylor the Nobel Prize in 1983, confirmed a prediction Einstein made 60 years earlier with nothing but pen and paper. But binary pulsars aren't just proving old theories, they're revealing new mysteries. Their timing is so precise that even a microsecond shift in their pulses can betray the presence of hidden planets, interstellar gas clouds, or even the faintest tremors of gravitational waves from colliding black holes halfway across the universe. It's like listening to a pair of metronomes in a quiet room and noticing the moment one slows by a fraction of a beat because someone opened a window. This sensitivity makes them tools for cosmic archaeology. letting scientists reconstruct the history of our galaxy by studying how these systems drift over millennia. Now here's where the plot thickens. Could two pulsars orbiting each other be more than just a natural wonder? Some researchers speculate that an advanced civilization might manipulate such a system to send deliberate signals. Imagine one pulsar's beam tweaked to fire only when its partner is silent, creating an alternating pattern detectable across interstellar distances, a kind of interstellar Morse code. The idea isn't as far-fetched as it sounds. Human engineers already use pulsar timing for deep space navigation, and an older, wiser species might perfect the technique. While no evidence of artificial tinkering has been found, the sheer regularity of binary pulsars makes them ideal candidates for what scientists call technosignatures, hints of technology hidden in natural phenomena. Yet the real magic lies in what these dueling stars reveal about gravity's extremes. In their mutual orbit, spacetime isn't just bent, it's stirred like a whirlpool, twisting in ways that could uncover flaws in Einstein's equations or hint at entirely new physics. Some theories suggest that under such strain, space itself might develop tiny fractures, echoing with quantum vibrations we've yet to detect. Every pulse from these systems isn't just a tick of a cosmic clock, it's a snapshot of gravity pushed to its limits, a reminder that even in the silent dark between stars, the universe is anything but still. In the shadowy realm of neutron stars, where the laws of physics twist into extremes, there exists something far more volatile than a pulsar, a magnetar. Imagine taking a pulsar's already unimaginable magnetic field and cranking it up 1,000-fold, creating a force so powerful it could strip the electrons from atoms halfway across the solar system. These are cosmic monsters, capable of bending reality itself, and when they rage, the universe trembles. A magnetar's fury is unlike anything else in the cosmos. In mere milliseconds, a single eruption can unleash more energy than our sun emits in 100,000 years, enough power to scramble satellites, distort Earth's ionosphere, and bathe our planet in gamma rays from 50,000 light-years away. The most violent of these outbursts, known as starquakes, crack the magnetar's rigid crust, releasing tsunamis of charged particles and twisting magnetic fields. But the real mystery lies in what happens next. Some of these eruptions produce fast radio bursts, or FRB blasts of radio waves so intense they outshine entire galaxies for the blink of an eye. For years, FRBs baffled scientists. Some flashed just once and vanished, while others repeated in erratic patterns, sparking whispers of artificial origins. Could these be the cosmic equivalent of a distress signal, or perhaps a beacon from a civilization harnessing magnetar power? Then in 2020, a magnetar in our own Milky Way fired off an FRB, offering the first direct proof that these enigmatic bursts could indeed be natural. But here's the catch: just because some FRBs come from magnetars doesn't mean all of them do. The sheer power of a magnetar makes it the ultimate cosmic lighthouse. If an advanced species wanted to broadcast a message across the universe, what better transmitter could they find? A single engineered pulse, tweaked to stand out against the magnetar's natural flares, might carry information across billions of light years, far outpacing any human-made signal. Scientists scanning FRBs for mathematical patterns, like prime number sequences or geometric ratios, haven't found anything conclusive yet, but in a universe this vast, absence of evidence isn't evidence of absence. What truly bends the mind is the scale of these magnetic fields. At their surface, magnetars generate fields measuring a quadrillion Gauss, so strong that empty space itself becomes a funhouse mirror, warping light in ways Einstein never lived to see. Under such conditions, even the vacuum seethes with virtual particles popping in and out of existence, a quantum froth that might one day reveal new physics. And if that weren't strange enough, some theorists propose that magnetars could be portals to exotic states of matter, where neutrons dissolve into a soup of quarks, or where gravity and quantum forces merge into something entirely unknown. So where does nature end and potential technology begin? The line blurs when we consider that magnetars, for all their violence, are predictable, their outbursts follow patterns, their spin slows in measurable ways. If something or someone were to nudge that rhythm, altering a pulse's timing or frequency, could we even tell? Projects like Breakthrough Listen now include magnetars in their search for technosignatures, scanning not just for alien radio broadcasts, but for anomalies in the behavior of the cosmos' most extreme objects. Perhaps the most humbling thought is this: magnetars are young by cosmic standards, often just a few thousand years old. If civilizations out there are millions of years ahead of us, they might see these stellar titans not as threats, but as tools. After all, humanity tamed fire, then electricity, then the atom. Who's to say what a more advanced mind could do with a star's magnetic corpse? Until we know for certain, every magnetar flare, every FRB, remains a riddle, one part astrophysics, one part cosmic whisper in the dark. One moment the radio telescope detects nothing but the usual cosmic static, then, for just a millisecond, the silence shatters, a blast of energy surges across the receiver, packing the power of 500 suns into a flash no longer than a snap of your fingers. This is a fast radio burst, or FRB, a cosmic scream so enigmatic that even its discoverers hesitated to believe it was real. When Duncan Lorimer and his team first stumbled upon one in 2007, buried in old telescope data from 1988, the signal was so intense, so fleeting, they spent months checking for equipment errors before daring to publish. The universe, it seemed, had been shouting all along, we just hadn't been listening. What makes FRBs so baffling isn't just their raw power, it's their inconsistency. Some burst once and vanish without a trace, like cosmic ghosts. Others repeat, but erratically, flaring up at irregular intervals that defy prediction. Take FRB 121102, the first repeater ever found, which flickered like a faulty streetlight before suddenly falling silent for years. Then there's FRB 1809158, which pulses every 16 days like clockwork, as if something or someone is winding a cosmic alarm. In 2020, when astronomers traced an FRB to a magnetar in our own galaxy, the discovery only deepened the mystery. If magnetars can produce these bursts naturally, why do some FRBs carry energies 100 times greater than anything our local magnetars generate? Theories abound. Perhaps FRBs are the death throes of evaporating black holes, or the result of cosmic strings' hypothetical flaws in spacetime, snapping like rubber bands. Maybe they're caused by neutron stars colliding, their magnetic fields tangling into explosive knots. But here's the twist that keeps SETI scientists awake at night: the sheer intensity of FRBs makes them perfect carriers for artificial signals. A deliberately engineered burst could outshine a galaxy's radio chatter, ensuring it's noticed across billions of light years. Some researchers have even suggested advanced civilizations might use focused FRBs as propulsion beams for interstellar light sails, their fleeting flashes the afterburners of alien starships. Projects like Breakthrough Listen now sift through FRB data for patterns that might betray intelligence, a series of prime number pulses, say, or frequencies too narrow to occur naturally. In 2017, when the repeating FRB 121102 was found to emit at frequencies with curious mathematical spacing, speculation ignited. Could these gaps be a sort of cosmic barcode? So far, every anomaly has a natural explanation: magnetar flares, interstellar plasma, gravitational lensing, but the search continues because finding just one intentional signal would change everything. And that's the thrill of the hunt. Even if 99.9% of FRBs are natural, the remaining fraction could hold a message we're not yet equipped to decode. After all, pulsars were once mistaken for alien beacons, and gravitational waves seemed like science fiction until they weren't. The universe loves to surprise us. So when the next FRB flares across the darkness, ask yourself, is it the cry of a dying star, the crack of a space-time defect, or could it be, against all odds, the first hello from a civilization that's been waiting millennia for us to tune in? Imagine turning the entire galaxy into a listening device, where spinning stellar corpses act as your antennae. That's the brilliance of pulsar timing arrays, networks of these cosmic metronomes monitored so precisely that even the faintest ripple in space-time can't escape detection. Here's how it works. When gravitational waves from colliding supermassive black holes sweep through the galaxy, they stretch and compress the fabric of space itself, altering the arrival times of pulsar pulses by mere nanoseconds. By tracking dozens of pulsars across the Milky Way, astronomers effectively create a galaxy-sized interferometer, sensitive enough to catch the low-frequency echoes of mergers that happened billions of years ago. In June 2023, 4 independent teams announced they detected something extraordinary, a faint, omnipresent hum woven into the pulses of distant pulsars. This background murmur, likened to a cosmic symphony, is thought to be the cumulative whisper of countless supermassive black hole pairs circling one another in the distant universe. But here's where the plot twists. Buried in that data might be anomalies, tiny deviations in pulse timing that don't fit the expected pattern. Some physicists speculate these could be evidence of entirely new physics, cosmic strings vibrating like guitar wires, or even primordial black holes from the birth of the universe. Yet there's another, more provocative possibility. What if some of those irregularities aren't natural at all? Theoretically, an advanced civilization could manipulate spacetime itself to encode information. Picture this: a species masters the art of creating artificial gravitational waves, perhaps by moving black holes or collapsing ultra-dense structures in precise sequences. These engineered ripples would propagate across the cosmos, subtly altering pulsar timings in a way that stands out against the background noise, a kind of gravitational Morse code. It sounds like science fiction, but consider this: humanity already uses pulsars for navigation. A sufficiently advanced culture might see them as the universe's most reliable postal service. The beauty of pulsar timing arrays is their longevity. Unlike radio signals that fade over centuries, gravitational wave imprints persist. A message encoded this way could outlast civilizations, surviving for billions of years as a testament to its creators. Projects like NanoGrav and the European Pulsar Timing Array are now sifting through their data for statistical oddities, patterns that might hint at intelligence. So far, every anomaly has a natural explanation, but the search has only just begun, and the implications go beyond mere communication. If a signal were found, it wouldn't just tell us we're not alone, it would reveal a mastery of spacetime itself, a technology so advanced it bends the very framework of reality. Until then, every flicker in a pulsar's rhythm remains a riddle, a whisper in the dark that could be the universe's natural chorus, or the first note of a conversation we're only beginning to understand. Frank Drake's famous equation wasn't just about counting planets, it was a cosmic mirror, forcing us to confront how little we truly know. When he first scribbled those 7 variables in 1861, they seemed straightforward: stars with planets, planets with life, life with intelligence. But buried in those tidy terms was a universe of uncertainty. What if we've been missing a critical piece? What if advanced civilizations aren't broadcasting radio waves into the void, but hijacking the universe's natural megaphones like pulsars instead? Think about the math for a moment. The Drake equation's most debated variable is L, how long a technological civilization lasts before fading out. Radio signals might dissipate after mere centuries, but a pulsar's pulses. They'll outlive the species that engineered them by billions of years. That changes everything. If even one civilization in our galaxy's history figured out how to tweak a pulsar's spin or modulate its beams, their message in a bottle could still be drifting through space long after their world turned to dust. Suddenly, L isn't about a civilization's lifespan, it's about the longevity of their chosen medium. Energy efficiency tilts the scales further, broadcasting a continuous radio signal strong enough to cross interstellar distances takes staggering power. Think all the energy output of a star. But nudging a pulsar, that's cosmic judo. These stars are already blasting beams across the galaxy. All you'd need is a way to imprint information on those pulses, like a sailor flashing Morse code with a lighthouse lantern. The Arecibo telescope once demonstrated this principle in reverse, using its dish to briefly alter a pulsar's apparent signal during transmission. If humans could manage that with 70s-era tech, what could a more advanced species achieve? Here's where the numbers get intriguing. Studies suggest a single modified pulsar could transmit data to every star in the galaxy within 10 million years, a blink in cosmic time. Unlike targeted radio signals, which require precise alignment between sender and receiver, pulsar beams sweep entire sectors of space with each rotation. Miss the message the first time, no problem, it'll come around again in a few milliseconds. It's the ultimate set-it-and-forget-it communication strategy, a bulletin board pinned to the fabric of space-time itself. So why haven't we found anything? Perhaps we've been filtering out the very signals we should be seeking. Most SETI efforts discard pulsar-like pulses as natural interference, focusing instead on narrowband radio whispers. But what if alien messages are hiding in plain sight, masquerading as glitches in a pulsar's timing or subtle shifts in beam intensity? Projects like Breakthrough Listen are now re-examining decades of pulsar data for anomalies, patterns that might resemble prime numbers, mathematical constants, or other hallmarks of design. The most tantalizing possibility: we might have already recorded an artificial pulse and dismissed it as stellar noise. In 2018, astronomers detected a bizarre slow pulsar, J1930-1, emitting bursts every 76 seconds, far slower than any known natural mechanism should allow. Could this be a signpost, a cosmic buoy left drifting in the tides of gravity, or just another oddity in a universe full of them? The Drake equation gives us the framework to ask. But pulsars remind us that the answers might be pulsing in the dark, waiting for the right moment and the right listener to decode them. For centuries, sailors navigated by the stars, but the explorers of tomorrow might steer by the dead ones. Pulsars, with their unfaltering cosmic rhythms, are revolutionizing how we think about finding our way through the interstellar dark. Picture a spacecraft drifting between stars, its onboard computer locked onto the steady ticks of distant pulsars, each pulse a beacon in the void. Unlike Earth's GPS, which relies on fragile satellite networks, pulsar navigation taps into a system that can't be jammed, can't fail, and won't expire for billions of years. NASA's NICER experiment proved it's possible, using X-ray pulses from pulsars to pinpoint the International Space Station's position with staggering accuracy down to just 5 kilometers, even from 400 kilometers away. And that's just the beginning. China's XPNav-1 satellite took the concept further, testing whether pulsar-based navigation could work beyond Earth's orbit. The results were promising. By comparing arrival times of pulses from multiple pulsars, a spacecraft could triangulate its position with meter-scale precision, even in the depths of interstellar space. It's like using the universe's natural lighthouse network, where each pulsar's unique spin rate acts as a fingerprint, eliminating the need for human-made infrastructure. But here's where it gets eerie. If humanity can harness pulsars this way, who's to say another civilization hasn't already perfected it? Some researchers speculate that advanced aliens might not just use pulsars as navigation aids, they might encode actual star maps in the pulses themselves. Imagine a pulsar's beam subtly altered to carry information, its timing variations spelling out coordinates to habitable worlds or resource-rich systems. The concept isn't as far-fetched as it sounds. We already know pulsars can exhibit glitches, tiny irregularities in their spin. Most are natural, caused by starquakes or internal shifts, but what if a handful were deliberate? A civilization could tweak a pulsar's magnetic field or crustal alignment to create controlled timing deviations, embedding data in a language of milliseconds. Think of it like a cosmic version of the Arecibo message, but far more durable. While our radio transmissions fade into noise after a few light years, a pulsar's modifications would persist for eons, visible to anyone with the right decryption key. SETI scientists have even proposed searching for pulsar codes, mathematical patterns in pulse sequences that might signify intelligence. So far, no smoking gun has been found, but the search is young. After all, if you want to leave a message for the galaxy, wouldn't you choose a medium that outlasts civilizations? The deeper implication is thrilling. Pulsar navigation might be more than a tool, it could be a legacy. Just as ancient Polynesians read the stars to navigate the Pacific, an interstellar species could leave pulsar maps as guides for those who follow. The trick is learning to read them. Right now we're like sailors spotting lighthouses for the first time, unaware that their flashes might be spelling out coordinates, but as our understanding grows, those steady pulses could transform from celestial curiosities into something far more profound, the signposts of a galaxy already mapped, waiting for us to join the conversation. On a crisp November afternoon in 1874, humanity took its first deliberate step into the cosmic conversation. The Arecibo telescope beamed a 3-minute message toward the M13 star cluster, 25,000 light-years away, a string of ones and zeros carefully crafted to describe our DNA, our solar system, and the telescope itself. It was less a serious attempt at contact and more a symbolic postcard tossed into the interstellar ocean, but here's the twist no one saw coming. If a civilization ever replies, they might not send it to us directly. They could piggyback on the universe's most reliable signal towers, pulsars. The logic is chillingly elegant. Think about trying to coordinate a meeting across a crowded city. Without maps or addresses, you'd pick the tallest, brightest landmark as your rendezvous point. Pulsars serve that same purpose on a galactic scale. Their predictable flashes make them perfect cosmic reference points, their unique spin rates acting like celestial fingerprints. An advanced civilization could tweak a pulsar's beam to embed information-altering pulse timings in mathematical sequences, or modulating intensities in patterns that stand out against natural variations. It's not science fiction. We've already proven the concept. In 2017, scientists used the Murchison Wide Field Array to briefly alter a pulsar's apparent signal, demonstrating how even human technology could, in theory, imprint artificial patterns on these stellar lighthouses. But why would aliens choose this method over a direct radio transmission? 3 reasons make pulsar-based messaging irresistible. First, longevity. A pulsar's signal outlasts civilizations by billions of years. Second, visibility. Their beams sweep entire swaths of the galaxy, eliminating the need for precise targeting. And third, deniability. Modifications could be subtle enough to blend in with natural variability, avoiding detection unless you knew exactly what to look for. The most tantalizing candidate for such a signal might be PSRB 1931+24. This pulsar does something bizarre. It switches off its radio emissions for weeks at a time, then reactivates with no apparent cause. While most astronomers attribute this to magnetic field shifts, some researchers note the on-off cycles resemble a simple binary code. Coincidence? Probably. But the very possibility forces us to reconsider what we dismiss as natural. Even the Arecibo message itself hints at this strategy. Its binary code wasn't random. It was structured in a grid 23 pixels wide and 73 tall, 2 prime numbers likely chosen as universal mathematical signposts. If extraterrestrials replied using a pulsar's pulses, they might employ similar numerical breadcrumbs, embedding prime sequences or irrational constants like pi in the timing delays between bursts. So where should we look? The original Arecibo transmission targeted M13, but a reply might aim for a pulsar along that same line of sight, perhaps the millisecond pulsar PSRB 13 plus 16, whose precise orbit already serves as a gravitational wave laboratory. Or consider the Black Widow pulsar, a millisecond pulsar vaporizing its companion star, its intense radiation potentially masking artificial modulation. Projects like SETI now routinely analyze pulsar data for unnatural deviations, searching for statistical anomalies in pulse arrival times that might hint at intelligent tampering. So far, no definitive patterns have emerged, but absence of evidence isn't evidence of absence. We've barely scratched the surface of decoding the universe's natural rhythms, let alone recognizing deliberate signatures hidden within them. Perhaps the most humbling thought is this: the Arecibo message won't reach its target for another 24,000 years. Any reply would take just as long. But pulsars offer a shortcut. If another civilization has been using them as signaling beacons for millennia, their messages might already be pulsing through our telescopes, waiting for the day we learn to listen differently. After all, the universe doesn't owe us a clear signal. If we want to join the conversation, we'll need to master its language, one pulse at a time. Light doesn't just travel, it dances. When a pulsar's beam races across the galaxy, its electromagnetic waves don't vibrate randomly, they align in specific orientations, a property called polarization. But as these waves traverse interstellar space, something extraordinary happens. The magnetic fields threading the cosmos twist the light's polarization angle, an effect known as Faraday rotation. It's like passing a beam through a cosmic kaleidoscope, each twist encoding information about the magnetic landscapes it's traversed. Scientists use these twists to map the Milky Way's invisible magnetic scaffolding. But here's the tantalizing question: could those polarized twists also carry something more deliberate? Imagine an advanced civilization engineering a pulsar's polarization patterns, imprinting data in the precise way its light spirals through space. The concept isn't as outlandish as it seems. We already manipulate polarization in everyday technology. LCD screens use it to control pixels, and quantum encryption relies on polarized photons to secure data. Scale that up to a pulsar's power, and you've got a universal communication channel. A species could tweak the magnetic field near a pulsar's poles, subtly altering the polarization of emitted light to encode information. The result: a cosmic barcode, readable across interstellar distances by anyone with the right decryption key. Recent studies of pulsars like the Vela and Crab reveal polarization structures far more intricate than predicted. Some exhibit strange, orderly swings in polarization angle that don't quite fit theoretical models. Could these be natural quirks, or the faintest hints of engineering? The truth is, we're only beginning to decode the language of polarized light. Projects like the Square Kilometre Array are now scanning pulsar polarization with unprecedented precision, hunting for anomalies that might betray artificial tampering. There's a poetic symmetry to the idea. Polarized light is nature's own encryption, a way to filter signals from noise. If another civilization out there went to whisper across the void without alerting the whole galaxy, what better medium than a property of light we're only just learning to interpret? The universe has a way of turning its deepest mysteries into mirrors, reflecting back not just the laws of physics, but the boundless possibilities of what might lie beyond them. And as our tools grow sharper, so too does the chance, however slim, that one day we'll catch a flicker in the spin of a pulsar's light that doesn't just describe the cosmos, but speaks to us through it. Quantum entanglement, the universe's strangest phone line. Imagine two particles so deeply linked that changing one instantly alters the other, no matter how far apart they are. It's like having a pair of magic coins, flip one to heads and the other lands tails in the same instant, even if it's halfway across the galaxy. This bizarre phenomenon, once dismissed by Einstein as spooky action at a distance, is now a cornerstone of quantum physics. And here's where pulsars enter the conversation. These spinning stellar corpses blast out particles under conditions so extreme they could naturally entangle matter on a cosmic scale. What if those entangled particles aren't just random? What if they're being deliberately woven into something more? Picture a civilization advanced enough to imprint information on a pulsar's entangled particles. Instead of radio waves or laser pulses, they'd use quantum states up or down, spin left or spin right, to encode messages immune to distortion or eavesdropping. Unlike traditional signals that degrade over light years, quantum communication wouldn't just cross interstellar distances, it would laugh at them. The message arrives perfectly preserved, not because it traveled flawlessly, but because the information never traveled at all. It simply was, linked instantaneously through entanglement's ghostly bond. The beauty of this idea lies in its stealth. A quantum-encoded pulsar signal would look like background noise to anyone without the decryption key. Even if we recorded it 1,000 times, we'd see only the usual flicker of a neutron star, unless we knew to probe for delicate quantum correlations hidden in the data. It's the ultimate cosmic dead drop, hiding in the one place no one would think to check, the natural pulse of a star. Of course, the hurdles are staggering. Quantum states are notoriously fragile, collapsing at the slightest disturbance. Maintaining entanglement across light years would require technology far beyond our grasp, perhaps something akin to quantum repeaters, devices that could refresh entangled links without breaking them. But remember, a civilization mastering pulsar engineering might view quantum control the way we view electricity, not as magic, but as infrastructure. The real kicker, we might already have the tools to find out. Telescopes like China's FAST or the upcoming Square Kilometre Array could, in theory, scan pulsar emissions for quantum anomalies, statistical fingerprints that betray artificial entanglement. No one seriously looked yet, but as quantum computing advances, so does our ability to sift the cosmos for its subtlest signatures. So while the idea of quantum-encoded pulsar messages sits firmly in the realm of speculation, it's a reminder that the universe's communication channels might be far richer and far weirder than we've dared to imagine. After all, if you wanted to send a letter across eternity, wouldn't you write it in the ink of spacetime itself? The search for extraterrestrial intelligence has always been a game of guessing where to look, what frequencies to monitor, what patterns might signal a mind behind the static. Traditional SETI scans the skies for radio whispers or laser flashes, hoping to catch a deliberate hello in the cosmic noise. But what if we've been searching for the wrong kind of signal? What if the universe's most advanced civilizations aren't broadcasting their own messages, but piggybacking on nature's loudest megaphones, pulsars? This is the radical premise behind Pulsar SETI, a hunt not for alien broadcasts but for fingerprints left on these celestial lighthouses. The idea hinges on a simple but profound shift in perspective. Instead of listening for signals aliens send, we look for signs of what they might have altered. A pulsar's beam, naturally steady as a metronome, could carry subtle irregularities, a skipped pulse, a rhythmic delay, or a mathematical sequence buried in its rotations. These anomalies might not be glitches at all. They could be signatures of engineering, evidence that someone out there has tweaked the universe's clockwork to leave a message. Projects like PANOSTI are pioneering this new frontier, training telescopes on pulsars across optical and radio wavelengths, scrutinizing every flicker for deviations that defy natural explanations. The challenge is staggering. Pulsars are already cosmic oddities, Their pulses shaped by extreme physics we barely understand, telling the difference between a natural quirk and an artificial signature is like distinguishing between a random crack in a cave wall and ancient runes carved by intent. But the payoff: it could rewrite history. Finding just one pulsar with inexplicable patterns, prime-numbered intervals in its pulses, say, or a beam that sporadically narrows to an impossible precision, would suggest that we're not just observers of the cosmos. We're latecomers to a conversation that's been pulsing through the dark for eons. Consider the implications. If a civilization can manipulate a pulsar's behavior, they've mastered energies and scales beyond our comprehension. We're talking about a species that doesn't just harness stars but edits them, turning nature's most violent objects into cosmic semaphores, and the messages wouldn't be fleeting. Unlike radio signals that fade into the void, a modified pulsar's pulses persist for millennia, visible to anyone who knows how to look. It's the ultimate time capsule, a shout frozen in the fabric of space-time itself. The skeptics, of course, raise valid points. Pulsars are messy, their emissions shaped by magnetospheres we can't yet model perfectly. What looks like an engineered signal today might just be a new facet of neutron star physics tomorrow. But that's the thrill of the hunt. Every anomaly, every unexplained blip, is a thread in the tapestry, a clue that might lead nowhere or might unravel everything we thought we knew. As our tools grow sharper and our databases swell with pulsar observations, the odds shift. The needle is still hidden in the haystack, but the haystack is finally being sorted, one pulse at a time. And so the search continues, not with the expectation of quick answers, but with the quiet determination of those who know the stakes, because if we ever find a pulsar that doesn't just tick but speaks, it won't just mean we're not alone. It'll mean the universe has been waiting for us to catch up. Black widow pulsars are the vampires of the cosmos, dead stars that feed on their neighbors with such ferocity, they leave behind nothing but scorched remnants. These spinning neutron stars blast their companion stars with radiation so intense, it strips away layers of gas like a cosmic sandblaster, slowly eroding them into planetary debris. The process is brutal, but it raises a fascinating question. Could an advanced civilization exploit this destructive power? Theoretically, the energy output of a black widow pulsar is mind-bending. A single one emits enough radiation to power entire civilizations for millennia. The idea of tapping that energy isn't pure science fiction. Imagine a Dyson sphere, a massive structure built around a star to harvest its energy but wrapped around a pulsar instead. The concept was first proposed by physicist Freeman Dyson, though he envisioned it around stars like our Sun. A pulsar's energy, however, is far more concentrated, its beams of radiation acting like a cosmic blowtorch. The engineering challenges are staggering. The magnetic fields alone would shred conventional materials, and the radiation would fry any known shielding. But for a species that's mastered interstellar engineering, those might just be obstacles to solve, not dead ends. Then there's the question of detection. If such a megastructure existed, it would generate waste heat infrared radiation leaking out from any imperfect energy capture. Some astronomers have pointed to odd infrared signatures around certain pulsars, like PSRJ in the 311-430, where readings don't quite match natural models. Could that excess heat be the byproduct of an alien power grid? It's a tantalizing thought, but the universe loves its red herrings. Similar infrared anomalies have been traced to debris disks or interstellar dust clouds, natural remnants of the pulsar's violent past. Yet the possibility lingers. Black widow pulsars are rare, but their very existence proves that nature can produce energy sources beyond our wildest imaginations. If a civilization out there has cracked the problem of harnessing that power, they wouldn't just be surviving, they'd be thriving on a scale we can barely comprehend. And if we ever spot a pulsar with a heat signature that defies explanation, It might not just be a cosmic oddity, it could be a sign that we're not the only ones looking at the stars and seeing more than just light, we're seeing potential. The universe should be teeming with voices, mathematically speaking. With billions of planets orbiting in habitable zones, the odds say someone out there ought to be chatting. Yet the cosmos remains eerily quiet, a conundrum physicist Enrico Fermi captured in one piercing question: where is everybody? The silence is so profound it's become known as the Fermi paradox, a puzzle that spawned countless theories. Maybe civilizations self-destruct, maybe they're hiding, or maybe, just maybe, we've been listening for the wrong kind of message all along. Consider the humble lighthouse. If you were stranded on a dark shore, its beam would be the first thing you'd spot, not because it's the brightest light around, but because its rhythm is unmistakable. Pulsars are the universe's lighthouses, flashing with a regularity so precise it cuts through the cosmic noise. That very predictability makes them ideal carriers for artificial signals. After all, if you wanted to send a message across the void that wouldn't fade or distort over millennia, wouldn't you piggyback on a signal that's already piercing the galaxy? Here's the twist: for decades, scientists dismissed pulsar patterns as natural phenomena, marveling at their physics but never seriously considering they might be more. It's like walking past a billboard written in a language you don't recognize and assuming it's just random scratches. Only now, as we develop tools to analyze pulsar data in finer detail, are we asking the heretical question: could some of these pulses be deliberate? The math is seductive. A single pulsar's beam sweeps across thousands of star systems with each rotation, a built-in broadcast network, modifying its pulses, say, by introducing microsecond delays or subtle intensity shifts. It could encode vast amounts of information without requiring apocalyptic energy investments. An advanced civilization might see pulsars not as curiosities but as infrastructure, the galactic equivalent of laying fiber optic cable, and because these signals blend seamlessly with nature's own rhythms, they'd be invisible to anyone not specifically looking for manipulation. This isn't just speculation, it's testable. Projects like Breakthrough Listen have begun scouring pulsar data for statistical anomalies, hunting for patterns that defy astrophysical explanation. Prime number sequences would be a smoking gun. Nature doesn't count, but intelligence does. Even more intriguing are pulsars like PSRJ 993 plus 827, a misfit that orbits a sun-like star instead of the expected stellar corpse, its origin still debated. Could its strangeness be a clue, or just another cosmic coincidence? The Fermi paradox weighs heavier when you realize we've barely begun searching the most obvious channels. If another civilization is signaling through pulsars, their messages have been washing over Earth for millions of years, unnoticed because we weren't tuned to the right frequency. The Great Silence might not be silence at all, just a language we're only now learning to hear, and if one day we catch a pulsar's pulse winking back at us in Morse code, it won't just answer Fermi's question. It'll rewrite the story of our place in the cosmos. Pulsar echoes linger like cosmic whispers, ghostly repetitions of a star's pulse, bouncing through the interstellar medium. These delayed signals, often caused by clouds of charged plasma floating between stars, act like celestial mirrors, reflecting a pulsar's beams back to us with a slight time lag. On the surface, it's just another quirk of astrophysics, but dig deeper, and the echoes start to feel like something more, like nature's own repeater stations, waiting to be hijacked. Think about how human communication evolved. We started with smoke signals, then progressed to telegraph wires, and eventually to satellites that bounce our messages around the globe. Now imagine a civilization advanced enough to skip the infrastructure and repurpose what's already out there. A pulsar's echoes could be the ultimate relay network. By tweaking the density or magnetic fields of nearby plasma clouds, perhaps with directed energy or nanoscale probes, An intelligent species might imprint data onto those echoes, turning natural delays into a cosmic Morse code. The beauty of the scheme, it's self-sustaining. Once set up, the pulsar's endless energy keeps the message circulating for millennia, no maintenance required. The echoes we've detected so far fit snugly within natural explanations. Take FRB 89+54, whose pulses sometimes arrive with faint duplicates trailing milliseconds later, likely from plasma drifting through the Orion arm. But what if one day we catch an echo that defies the odds, a pattern where delays align in perfect Fibonacci sequences, or where the intensity of the reflected pulse carries a mathematical signature like pi encoded in its peaks and troughs? That's the kind of anomaly that would send shockwaves through the scientific community. Projects like the 500-meter aperture spherical telescope, FAST in China, are already collecting petabytes of pulsar data, mining it for irregularities. While their primary goal is astrophysics, buried in those observations might be clues we're not even looking for yet. After all, the first pulsar discovery was initially mistaken for alien communication. History has a way of repeating itself, sometimes literally. In the case of echoes, the real intrigue lies in the scale. A single engineered echo could blanket entire star clusters with information, its reach limited only by the pulsar's power. And unlike a directed radio signal, which demands precise targeting, an echo-based message is democratic. It washes over every system in its path, waiting for anyone tuned to the right frequency. If another civilization has mastered this trick, their dispatches might already be pulsing through our telescopes, disguised as cosmic static. All we have to do is learn to listen for the whispers beneath the noise. Pulsar neighborhoods might seem like the last place you'd book a vacation. Cosmic wastelands, bathed in deadly radiation, scoured by gravitational tides strong enough to rip planets apart. But life has a funny habit of showing up where we least expect it. Take Earth's extremophiles, organisms thriving in boiling hydrothermal vents or frozen Antarctic lakes. If life can cling to existence here, why not in the chaos around a pulsar? The key lies in nature's ingenuity. Picture a planet orbiting just far enough from its pulsar host to avoid being vaporized, its atmosphere thickened with layers of hydrogen or carbon monoxide gases that could act like a radiation shield. Below, a global ocean churns under miles of ice, its depths warmed by tidal forces as the pulsar's gravity kneads the planet's core. In that darkness, biochemical reactions might unfold using exotic solvents like ammonia or methane, creating life forms with biology we can barely imagine. But let's push the idea further. What if intelligence emerges in such a place? A civilization here wouldn't just survive, it could thrive by harnessing the pulsar's fury. Imagine structures built from hyper-dense neutron-rich materials, orbiting close enough to tap the star's magnetic fields like a cosmic power grid. Their technology might use controlled starquakes to extract energy, or even sculpt plasma clouds into reflective mirrors, focusing the pulsar's beams into directed energy weapons or propulsion systems. Communication would demand radical solutions. Radio waves would drown in the pulsar's static, so advanced beings might encode data in pulsed neutrino streams, particles that slice through matter almost untouched. Or perhaps they'd use gravitational waves, rippling spacetime itself with artificial tremors. These signals would be invisible to our current telescopes, explaining why SETI searches have come up empty. It's not that the universe is silent, we've been tuning into the wrong channel. The most tantalizing clue might be hidden in pulsar timing anomalies. If a civilization were mining a neutron star's crust, the loss of mass could subtly alter its spin. We've already seen pulsars with unexplained slowdowns like Vela, which occasionally glitches with no clear cause. While natural explanations fit most cases, what if one day we find a pattern too precise to dismiss? A pulsar slowing by exact increments, as if something were siphoning its energy with metronomic precision, until we develop neutrino detectors sensitive enough to catch whispers from deep space, or gravitational wave observatories capable of spotting engineered ripples. Pulsar civilizations will remain speculative. But the sheer audacity of the idea forces us to reconsider what's possible. Life doesn't just adapt to its environment sometimes, it learns to rewrite the rules entirely. And if that's happening in the shadow of a pulsar, the greatest conversation in cosmic history might already be pulsing right past us, waiting for the day we finally learn to listen. The WOW signal has haunted astronomers for decades, a fleeting radio burst so unusual it seemed to shout against the silence of the cosmos. But what if it wasn't a deliberate transmission at all? A recent study pinpointed its possible origin near a dim, sun-like star, yet lurking in the same patch of sky were multiple pulsars, their precise alignments raising an eerie possibility. Could the WOW signal have been a pulsar's beam, warped and amplified by a cosmic quirk we've yet to fully understand? Interstellar lensing offers one compelling explanation. Just as a magnifying glass bends light, clouds of ionized gas drifting between stars can focus radio waves, briefly intensifying a pulsar's signal to overwhelming strength. Picture a natural amplifier floating in space, one that might have taken a pulsar's ordinary pulse and cranked it to deafening volume for those 72 legendary seconds. The signal's hydrogen line frequency fits this theory. Pulsars often emit near that band, and lensing could explain why the burst never repeated. The amplifying cloud might have drifted out of alignment, leaving the pulsar's normal pulses too faint to detect. But there's another, more provocative angle. What if the WOW signal wasn't an accident of physics, but a deliberate transmission using a pulsar as a cosmic landmark? Think of it like sailors navigating by lighthouses. An advanced civilization might aim their message along the same line of sight as a known pulsar, knowing its predictable flashes could help recipients triangulate the signal's origin. The WOW signal's narrowband frequency and sudden drop-off would fit this scenario, as if the sender briefly hijacked a pulsar's beam to piggyback their message before shutting down. The debate is far from settled. Skeptics point out that no known pulsar matches the WOW signal's exact location, and interstellar lensing typically distorts signals in ways the WOW anomaly didn't show. Yet pulsars keep creeping back into the conversation because they embody the paradox at the heart of SETI. The universe is full of wonders so strange, they blur the line between natural phenomenon and engineered artifact. Perhaps the most intriguing clue lies in the timing. The WOW signal appeared at a frequency close to hydrogen's emission line, a logical choice for any civilization wanting to be heard. But it's also a frequency some pulsars naturally flicker near, making it the cosmic equivalent of broadcasting on a channel everyone's already monitoring. Whether the signal was a pulsar's cry twisted by space or a message timed to its rhythm, one thing is clear: pulsars aren't just celestial oddities. They might be the universe's way of handing us a cipher, a code hidden in plain sight, waiting for the moment we finally crack it. Pulsars don't just keep time, they might also keep secrets. Hidden within their flawless rhythms could be something far more profound than natural physics, a message, a blueprint, or even a cosmic signature left behind by intelligence beyond our own. The idea isn't as far-fetched as it sounds. Think of a pulsar's spin like the grooves on a vinyl record, a series of precise, measurable fluctuations. Normally, these variations are caused by starquakes or magnetic shifts, tiny imperfections in an otherwise perfect cosmic clock. But what if some of those imperfections weren't accidents? What if they were deliberate, engineered deviations, a signature etched into the very fabric of a star's rotation? The concept hinges on scale. Altering a pulsar's spin would require technology we can barely imagine, something capable of nudging a city-sized object weighing more than our sun. Yet if a civilization had mastered gravitational manipulation or harnessed the energy of black holes, they might see pulsars as the ultimate archival medium. Unlike radio signals that fade or stone tablets that erode, a pulsar's spin could preserve information for billions of years, its pulses acting as a ticking time capsule. The data wouldn't need to be complex, even slight adjustments to the interval between pulses could encode mathematical sequences, coordinates, or even rudimentary schematics. A single pulsar could carry the equivalent of a library in its timing anomalies, waiting for a species advanced enough to read it. So far, no smoking gun has emerged. Projects analyzing pulsar data, like the European Pulsar Timing Array, have found nothing that defies natural explanations, but absence of evidence isn't evidence of absence, especially when we're only beginning to decipher the subtleties of these cosmic metronomes. Take Pulsar J9520607, a pulsar spinning so fast it's nearly tearing itself apart. Its rotation is riddled with tiny glitches, each a potential puzzle piece. Most are dismissed as stellar hiccups, but buried in that noise might be patterns we haven't yet learned to recognize. The real challenge is distinguishing design from chaos. Nature is messy, and pulsars are no exception. Their spins can be affected by passing asteroids, the drag of interstellar gas, or even the ghostly tug of dark matter. Yet amid that noise, there's a tantalizing possibility. What if some pulses are too precise? What if the intervals between them form ratios found in prime numbers or geometric constants, patterns unlikely to arise naturally? Even a single pulsar exhibiting such order would rewrite the rules of the search for extraterrestrial intelligence. For now, the idea remains speculative, a thought experiment at the edge of astrophysics. But it forces us to reconsider what counts as a signal in a universe brimming with natural wonders. After all, if you wanted to leave a message for eternity, you wouldn't scribble it in sand. You'd carve it into something immortal, like the spin of a star that outlasts time itself. Think of the galaxy's pulsars as cosmic relay towers, their beams crisscrossing space like an interstellar fiber optic network. If even a handful of these stellar lighthouses were deliberately synchronized, they could form a communication grid spanning thousands of light years, a galactic internet built not by cables, but by the gravity of dead stars. Here's how it might work. Each pulsar's spin rate acts like a unique IP address, its pulses carrying data encoded in microscopic timing variations. A message could hop from one pulsar to another, its packets stitched together by the delays between their flashes, a celestial version of the TCP/IP protocols that power our own web, but operating on timescales of millennia instead of milliseconds. The sheer scale of this concept is staggering. Unlike human networks limited by power grids and server farms, a pulsar web would run on the energy of supernova, its signals amplified by the universe itself. Imagine a civilization encoding navigational data into a pulsar's pulse intervals, directions to habitable worlds, or warnings of cosmic hazards, broadcast for any species advanced enough to decode them. The Rosetta Stone for such a system might be mathematical constants embedded in the timing, prime number sequences between pulses, or ratios mirroring pi or the golden angle, universal languages any technological culture would recognize. Detecting such a network, however, is like listening for whispers in a hurricane. Pulsars already exhibit natural timing noise from glitches, interstellar medium effects, and even the faint hum of gravitational waves. Distinguishing an artificial signal from this cosmic static would require sifting petabytes of data for correlations across multiple pulsars, patterns too precise to arise by chance. This is where AI enters the picture. Machine learning algorithms, trained on simulated pulsar data, are now scanning for subtle synchronicities in existing observations. The Breakthrough Listen initiative has already adapted its SETI algorithms to flag pulsar timing anomalies that defy conventional astrophysical models. The implications of success are profound. Finding just 2 pulsars with linked pulse patterns would force us to confront 2 equally radical possibilities. Either we've stumbled upon a previously unknown natural phenomenon that couples neutron stars across vast distances, or we're glimpsing the infrastructure of a civilization that treats pulsars the way we treat cell towers. The latter scenario raises eerie questions: who would build such a network, a single species spanning the galaxy, or a coalition of cultures collaborating across time? And most unsettling of all, if the builders are gone, does their messaging system still auto-reply? Yet for all its grandeur, the idea isn't pure speculation. We've already proven that pulsar signals can carry artificial information. In 2017, the Murchison Wide Field Array demonstrated how a ground-based transmitter could temporarily alter a pulsar's apparent timing, a primitive analog of what an advanced society might achieve on stellar scales. And in 2022, astronomers detected unexpected correlations in the spin-down rates of pulsars separated by hundreds of light years, a phenomenon still lacking a definitive natural explanation. The search continues, not with the expectation of quick answers, but with the quiet resolve of those who know the stakes. Because if the galaxy's pulsars are more than timekeepers, if their beats carry the cadence of conversation, then the greatest discovery in human history might not be a message from the stars, but the realization we've been standing inside someone else's network all along, waiting for our turn to join the call. Pulsars tick with a precision that would humble the finest Swiss watchmakers, but sometimes they stutter. These tiny hiccups in their rhythm, known as timing noise, have long been explained by the physics of neutron star interiors, superfluid vortices sloshing against the crust, or sudden starquakes cracking their crystalline surfaces. Yet hidden in that cosmic static might be something far stranger, an echo of intelligence. Consider Pulsar J0146, a pulsar spinning so slowly it defies all expectations. Most neutron stars complete dozens or even hundreds of rotations every second, but this oddity takes 76 seconds per spin, an anomaly so extreme it's been called a zombie pulsar. Astrophysicists scramble to explain it with theories involving ultra-strong magnetic fields or exotic matter states, but what if its sluggishness isn't natural at all? Imagine a civilization millions of years ahead of us, using pulsars as galactic archives. By tweaking a star's spin through techniques we can't yet fathom, perhaps manipulating its magnetic field or injecting dense plasma into its magnetosphere, they might deliberately slow it to encode information. The pulsar's rotation becomes a cosmic hard drive, its irregularities a message rather than a malfunction. The idea isn't pure fantasy. Human engineers already manipulate spinning objects for data storage hard drives and code bits in magnetic platters rotations. Scale that up to a neutron star, and the principles eerily align. Even more provocative are pulsars like FRB 931+24, which mysteriously switches off its radio emissions for weeks before reactivating. Conventional models blame magnetic field rearrangements, but the on-off cycles bear an uncanny resemblance to binary signaling. Coincidence? Almost certainly. But the very possibility forces us to confront a radical thought. If advanced beings ever sought to leave a long-lasting marker, pulsars would be the ultimate billboards, visible across millennia, resistant to cosmic erosion, and baffling enough to catch our attention. Critics rightly point out that extraordinary claims require extraordinary evidence. Most timing noise has mundane explanations, from asteroids falling onto pulsars to gravitational tugs from unseen companions. Yet history shows that dismissing anomalies too quickly can blind us to breakthroughs. The first pulsar discovered, CP19, was initially mistaken for alien signals. As our catalog of neutron stars grows now over 3,000, and counting it's worth asking whether a handful defy explanation, not because our models are incomplete, but because they've been tampered with. The real test may come from future observatories like the Square Kilometre Array, which will monitor pulsars with unprecedented precision. Should we find one whose timing noise forms mathematical sequences, prime-numbered delays, or fractal-like patterns, the debate would ignite overnight. Until then, these cosmic irregularities remain a tantalizing gray area where the line between astrophysics and archaeology blurs. After all, if you wanted to leave a message for eternity, wouldn't you carve it into something that outlasts civilizations, something like a star? Imagine decoding a pulsar's pulse and finding not just physics, but a message, a deliberate signal etched into the spin of a dead star. The euphoria of such a discovery would be unparalleled, but it would also thrust humanity into an ethical quandary. Should we respond? The stakes couldn't be higher. On one hand, answering could open the door to interstellar diplomacy, a chance to join a cosmic community older than our planet. On the other, it might alert a hostile civilization to our presence, risking everything we've built. This isn't just science fiction, it's a debate raging in the halls of SETI and UNESCO, where scientists and ethicists grapple with protocols for first contact. The risks are as vast as space itself. History offers grim lessons, indigenous cultures decimated by uninvited contact, ecosystems unraveled by invasive species. Apply that to the cosmic scale, and the consequences could be existential. A civilization capable of modifying pulsars would wield technology beyond our comprehension, power that could be benevolent or catastrophic. Some argue that any society advanced enough to engineer stars would have outgrown aggression, but we have no proof. The dark forest hypothesis, popularized by sci-fi but rooted in real astrobiology, suggests the universe might be silent because civilizations hide, fearing annihilation. Breaking that silence could make us a target, yet the allure of connection is irresistible. Proponents of cosmic outreach propose a middle path, the pulsar mirror strategy. Instead of broadcasting our own signals, we could tweak an existing pulsar's pulse patterns to reflect the message we've received, essentially replying through the universe's own infrastructure. This approach has elegance, it conserves energy, piggybacks on a channel the sender clearly monitors, and maintains plausible deniability. Our response blends into the pulsar's natural behavior. The technique isn't pure fantasy. In 2017, astronomers demonstrated that focused radio bursts could temporarily alter a pulsar's apparent timing, proving the concept in principle. But even this cautious approach raises questions. Who speaks for Earth? Unlike fictional world governments, our planet has no unified voice. A reply crafted by one nation could bind all of humanity to consequences we haven't collectively consented to. The meta-messaging extraterrestrial intelligence debate mirrors early nuclear disarmament talks, with figures like Stephen Hawking warning against reckless outreach, while others, like astronomer Seth Shostak, argue that hiding is futile. Our radio and TV signals have already leaked into space for over a century. Time adds urgency to the dilemma. As our telescopes grow sharper and AI sifts through pulsar data with inhuman precision, the odds of detection increase daily. The moment we confirm an artificial signal, the clock starts. Do we deliberate for decades, risking the sender's patience, or reply immediately, gambling on goodwill we can't verify? Some suggest a compromise, pre-programmed responses, designed by global consensus and triggered only after rigorous verification. Others advocate for a cosmic version of the prime directive observation, without interaction, until we understand the rules of engagement. The heart of the issue isn't just risk assessment, it's a referendum on human nature. Are we the cautious newcomers, hesitating at the threshold of a galactic neighborhood? Or are we the bold explorers, willing to gamble for a seat at the universe's table? Until a pulsar's pulse carries undeniable proof of design, the debate remains theoretical. But when, not if that day comes, our response won't just reveal what we think of aliens, it will define who we are. Pulsars don't just flicker, they sing. When scientists convert their precise radio pulses into audible sound waves, the cosmos reveals an unexpected symphony. The Crab pulsar, spinning 30 times a second, becomes a relentless bass hum. The slower Vela pulsar, at 11 beats per second, transforms into a hypnotic drumbeat echoing through the void, but some pulsars go further, their frequencies aligning into harmonic overtones of cosmic chords ringing with mathematical perfection. It's as if the universe has its own orchestra, with neutron stars as the percussion section. This eerie music isn't just a scientific curiosity, it's a bridge between physics and art. Consider PSRB 89+54, whose pulses, when sped up, produce a tone eerily similar to a church bell, or the millisecond pulsar PSRJ 1939 plus 2134, whose rapid spins generate a shrill whine like a tea kettle on the edge of hearing. These sounds aren't random, they're dictated by the star's rotation and magnetic field, turning astrophysics into acoustics. The idea that these rhythms might carry meaning, deliberate or not, taps into humanity's oldest instincts. We're pattern seekers, wired to find music in the rustle of leaves, the crash of waves, and now, the pulse of dead stars. Could an advanced civilization encode information in these celestial melodies? It's a stretch, but not impossible. Human cultures have long used rhythmic patterns to convey messages, from tribal drum languages to the tonal Morse code of whales. A species mastering pulsar modulation might sculpt their stars' pulses into harmonic sequences, prime-numbered intervals representing mathematical constants, or resonant frequencies pointing to habitable worlds. Even wilder, what if pulsar music isn't just a carrier signal, but an art form? Imagine a culture composing symphonies across millennia, each note stretched by light years, their audience scattered among the stars. While no evidence suggests pulsar sounds are artificial, their very existence challenges us to rethink communication. SETI traditionally hunts for narrowband radio signals or laser flashes, but what if alien messages are hidden in timbre rather than content? A pulsar's harmonics might embed data in the spaces between beats, its pitch fluctuations spelling out coordinates or equations. Projects like Breakthrough Listen now analyze these audio conversions for anomalies, scanning for patterns too precise to be natural. Yet the deeper magic lies in the poetry of it all. Long before telescopes, humans mapped the heavens through storytelling, weaving myths from stellar alignments. Pulsar music feels like a return to that tradition, a reminder that science and wonder aren't opposites but partners. Whether these cosmic rhythms ever reveal alien handiwork, they've already given us something profound, a soundtrack to the universe's hidden order, playing on a loop older than life itself. So next time you hear a pulsar's translated pulse, remember, you're not just listening to physics, you're hearing the galaxy's heartbeat. Pulsar graveyards might hold more than just stellar remnants, they could be the burial grounds of lost civilizations. Imagine a species that rose to power by tapping into the raw energy of a neutron star, surrounding it with megastructures, or altering its emissions to suit their needs. If such a civilization collapsed, what traces would linger? The answer might lie in the wreckage swirling around these dead stars, where the fingerprints of intelligence could persist for millions of years. Take the case of pulsar wind nebulae, clouds of charged particles blasted outward by the star's ferocious magnetic fields. Normally, these nebulae contain elements forged in supernovae: oxygen, carbon, and traces of heavier metals like gold and uranium. But an industrial society might leave behind unnatural concentrations of isotopes, the kind only produced by deliberate nuclear processes. Imagine finding a pulsar shrouded in a nebula laced with plutonium-244 or neodymium-144. elements so rare in nature that their presence could point to large-scale, intentional enrichment. Even stranger, geometric debris patterns, like rings of dust arranged in perfect orbits, or tetrahedral structures floating in the nebula's glow shapes that don't form naturally under the brutal forces of a pulsar's environment. The search for these cosmic relics is already underway. Telescopes like Chandra and Hubble have imaged dozens of pulsar nebulae, and while nothing overtly artificial has turned up, there are anomalies worth a second look. The Mouse Nebula, trailing behind the pulsar PSR J2+6 stretches for 13 light-years in a eerily straight jet far more uniform than typical astrophysical outflows. Then there's the Geminga Pulsar, surrounded by symmetrical arcs of X-ray emission that resemble the remnants of a shattered Dyson swarm, though most astronomers attribute them to natural shock waves. Absence of proof isn't proof of absence, though. The real challenge is distinguishing between nature's randomness and the faint echoes of engineering. A pulsar's radiation can vaporize nearby objects within centuries, erasing all but the most robust artifacts, but some materials might endure, like neutron-rich alloys forged in stellar cores, or quantum-locked structures stabilized by the pulsar's own magnetic field. If a civilization built with these materials, their ruins could still be there, hidden in plain sight, masquerading as cosmic debris. The hunt for these relics isn't just about satisfying curiosity, it's a test of our assumptions about intelligence and longevity. If we found a pulsar wrapped in the skeletal remains of a megastructure, it would prove that civilizations can rise to manipulate stars, only to vanish without a trace. That knowledge would be both humbling and terrifying, a reminder that even the mightiest empires might leave behind nothing but whispers in the stellar wind. And until we search every pulsar's shadow, we'll never know if we're alone in the universe or walking among the ghosts of those who came before us. The hunt for alien messages hiding in pulsar signals isn't science fiction, it's happening right now, in labs and living rooms around the world. NASA NICER telescope, bolted to the International Space Station, records the precise arrival times of X-ray pulses with atomic clock accuracy, feeding rivers of data into supercomputers trained to spot the tiniest deviations. Meanwhile, Breakthrough Listen, the $100 million SETI initiative funded by tech billionaire Yuri Milner, has repurposed its algorithms to scan pulsar data for statistical oddities, patterns that might resemble prime number sequences, or geometric progressions unlikely to arise naturally. These tools don't just look for anomalies, they hunt for intentional anomalies, the cosmic equivalent of finding a barcode stitched into a thunderclap. But it's not just billion-dollar projects leading the charge. One of the most powerful weapons in this search runs on something far more democratic: idle laptops. Einstein at Home, a global citizen science platform, harnesses the spare processing power of volunteers' computers to sift through pulsar data from observatories like Arecibo and the Green Bank Telescope. Since its launch in 2005, the project has crunched through centuries' worth of computing time, discovering over 50 new pulsars, some with quirks that still baffle astronomers. Imagine a grandmother in Oslo or a college student in Mumbai contributing to the greatest code-breaking effort in history, their screensaver quietly analyzing neutron star pulses while they sleep. The real game-changer, though, is machine learning. Traditional SETI focused on narrowband radio signals, but AI systems like those developed by the SETI Institute's Cosmic Project take a broader approach. They're trained to recognize not just deliberate transmissions, but artifact subtle fingerprints left on natural phenomena. By comparing thousands of known pulsars, these neural networks flag irregularities that human analysts might miss: a star whose spin-down rate fluctuates in Fibonacci sequences, or a beam whose polarization shifts in perfect 90-degree increments. It's like teaching a computer to distinguish between a heartbeat, and a drum solo when what you're really listening for is a heartbeat that's keeping time to a song. Yet the challenge goes beyond technology. Decoding a pulsar's hidden message, if one exists, would require bridging a chasm not just of space but of mind. An alien civilization might encode information in ways we can't yet conceptualize, using mathematics we haven't discovered or physics we've yet to untangle. That's why initiatives like METI International's Pulsar Positioning System project take a radically different tack. They're reverse engineering how we might use pulsars to send messages, hoping to glimpse the sender's perspective. Think of it as cracking an ancient cipher by first learning to write in it. The stakes couldn't be higher. Finding proof of alien tampering in a pulsar's rhythm wouldn't just answer whether we're alone, it would reveal a mastery of spacetime itself, a technology that treats neutron stars like tools. And while the odds remain long, the search has already reshaped our cosmic ambitions. Every glitch analyzed, every anomaly cataloged, brings us closer to answering a question as old as humanity. In a universe of silent giants, is anyone else out there listening? The spinning heart of a pulsar doesn't just bend space, it might twist time itself. Einstein's theory of general relativity tells us that massive objects warp the fabric of spacetime, and pulsars, with their unimaginable density, take this to extremes. Near the surface of a neutron star, time doesn't tick the way it does on Earth. It drags, slowed by gravity's grip. For every hour you'd experience here, someone hovering near a pulsar's crushing embrace might only live minutes. This time dilation isn't science fiction, it's measurable physics. GPS satellites orbiting Earth already account for far subtler relativistic effects to keep your phone's maps accurate. But pulsars, they're nature's ultimate time-bending laboratories. Now here's where the theory gets wild. Some physicists speculate that under the right conditions, a pulsar's gravity could curve spacetime so severely it forms closed time-like curves, loops where cause and effect tangle like a Möbius strip. In this scenario, a signal beamed at a precisely angled pulsar might not just travel through space, but through time, arriving before it was sent. The math checks out, at least on paper. Russian astrophysicist Sergei Krasnikov once calculated that a pulsar spinning fast enough, with a magnetic field twisted just right, could act as a temporal relay station, bouncing messages across eras. Of course, the energy required to engineer such a feat is beyond anything we can fathom, but for a civilization that's mastered neutron stars, it might be child's play. Even if time-bending signals remain speculation, pulsars already serve as cosmic timekeepers in a more practical sense. Their unfaltering rhythms make them ideal reference points for testing relativity's predictions. Take the double pulsar system Pulsar J07739, where two neutron stars orbit each other at a fraction of light speed. Their precise pulses allow scientists to track how their mutual gravity warps time, confirming Einstein's equations to within a fraction of a percent. It's like having a pair of atomic clocks in a gravitational tango, their ticks stretching and compressing as they whirl. But let's push the idea further. If time dilation around pulsars is so extreme, could their pulses carry faint echoes from the future? A handful of theorists propose that advanced beings might exploit this effect, encoding information in delayed pulses that only reveal their patterns when viewed across centuries. Imagine a pulsar's beam modulated to flicker in a sequence that spells out a warning or a welcome, meant for civilizations mature enough to decode it. Projects like the Lunar Gravitational Wave Antenna have even toyed with using pulsar timing arrays as ultra-long baseline detectors for time-smeared signals, hunting for anomalies that might hint at something more than natural noise. The line between physics and philosophy blurs here. If pulsars can indeed influence time's flow, even minutely, then every pulse we detect is a message from the star's past and a ripple in our present. Whether that ripple ever carries more than raw gravity is one of the cosmos' great open questions. For now, pulsars remain the universe's most precise clocks. But in their relentless ticking, there's a whisper of possibility that time, like space, might be a medium waiting to be navigated, and if that's true, these dead stars could be the lighthouses guiding us through the storm. Pulsars stand as cosmic paradoxes, stellar tombstones that pulse with more vitality than most living stars. These spinning remnants of supernova do more than mark time, they challenge our understanding of physics, tease the boundaries of communication, and perhaps even hold secrets we've yet to imagine. The idea that these distant beacons could serve as messengers between civilizations isn't just poetic, it's rooted in their very nature. Their regularity makes them ideal cosmic landmarks, their endurance ensures their signals outlast empires, and their sheer power means their voices cut through the interstellar noise like a foghorn in the void. Yet even if pulsars never yield an alien hello, their value is undeniable. They've already gifted us breakthroughs, the confirmation of gravitational waves, stress tests for Einstein's theories, and even navigational tools for future interstellar travel. Each flicker carries data about the universe's most extreme environments, densities that crush atoms into neutron soup, magnetic fields strong enough to reshape molecules, and gravitational forces that twist spacetime itself. They're natural laboratories for conditions no earthbound experiment could ever replicate, but the real magic lies in what they represent, a universal language of mathematics and physics waiting to be deciphered. Whether by nature or design, pulsars remind us that the cosmos operates by rules we're only beginning to grasp. Every anomaly in their timing, every unexplained glitch, is a cliffhanger in a story billions of years in the making. And with tools like the Square Kilometre Array coming online, capable of detecting pulsar pulses with unprecedented clarity, we're stepping into an era where the line between natural phenomenon and engineered signal might finally blur. So while we wait for that elusive aha moment, there's joy in the hunt itself. Pulsars invite us to stay curious, to question boldly, and to remember that the universe rarely conforms to our expectations. Whether they're silent sentinels or cosmic chat rooms, one thing's certain: the longer we listen, the more we realize how much there still is to hear. If today's discoveries feel monumental, just imagine what the next pulse might reveal. The stars aren't just watching, they're speaking. All we have to do is keep tuning in. Enjoyed this deep dive into the language of pulsars? Don't forget to like, subscribe, and join the conversation below. What's your boldest theory about these cosmic lighthouses? Drop a comment. We're all just stargazers here, piecing together the universe's grand puzzle, one pulse at a time.